All right, so we're going to find open intervals where our functions are increasing or decreasing. So first of all, if you are using interval notation with increasing and decreasing, you're going to need to remember to never, ever, ever use hard brackets. So with interval notation, you never use hard brackets. Okay, so why is that? If I go to the airport and if I watch an airplane take off, I can see the airplane going up, okay, because I watch it. It starts from down here and it goes up. So I can see that it is increasing in altitude. If I go to the airport, I can see that a plane is landing because it is going down. But if I take a picture, don't judge my drawing. If I take a picture of an airplane just sitting there, you cannot tell me if that airplane is going up or going down. So the same thing with a point in space. That point cannot go up or down. You have to tell me what the function is doing. So if you tell me that something is increasing from like 0 to 3 and you use hard brackets, then you're telling me that 0 itself is going up or down. And it can't do that. A single point cannot go up or down. So you never use hard brackets. You only use parentheses or soft brackets. All right, so I would like to know the largest open interval on which f is increasing. So I know that from here to here, my graph is going up. So I know from 0 to 4, he's increasing. Okay, so don't tell me y values. That tells me the actual height. I just want to know when it's moving in an upwards direction and when it's moving in a downwards direction when I'm reading left to right. I don't care how tall it gets or how low it gets. So from here to here, on this width, it's going up. From here until here, he's going down. So from this direction to this, or from 4 to 8, he's going down. And then from 8 to 9, he's going up. So from here to here. And then from 9 to 10, he's going down. Well, it wants the largest or the widest open interval. So of your options, that's the widest of the two where he's increasing. And of your options, that's the widest of the two where he's decreasing. So now you know how to do increasing, decreasing, which means you can do this one. Do not include 2. All right, so let's look at that for just a second, actually. It says find the largest open intervals where he's increasing and decreasing. So where is he decreasing? Well, from here, and I'm just going to use the axis, which is not really well marked. Okay, so here's your axis. All right, so from here until here, he's decreasing. And then again from 2 to 4. So from a -3 to a 2, he's decreasing. And then again from 2 to 4, he's decreasing. Because as I read it from left to right, he's going down. As I read it from left to right, he's going down. So why do I have to put this here? The function does not exist at 2. There's an asymptote there. So you can't tell me that something is decreasing when it doesn't exist. Okay, so for right now, he's decreasing from -3 to 2. And then again from 2 to 4. He's increasing from 4 to 5. And then he's decreasing from 5 to 6. And then he's increasing. Wait a minute, what did I just say? Hang on. He's increasing from 4 to 5. He's decreasing from 5 to 6, sorry. And then he is increasing from 6 to 7. So of those options, which one is the widest? Well, on this one, this is going to be your widest. On this one, these match. So they are both 1 unit wide. And so you'll have both of those. So he is increasing from 4 to 5 and from 6 to 7. All right, so what we have is, I would like to estimate the open intervals on which he's increasing or decreasing. So you know that he's going to stop right here. So from left to right, he's going to be increasing. Remember, you're telling me width, not height. So from negative infinity until I hit negative 3, he's going up. So from negative infinity to negative 3. And then from negative 3 to positive infinity, he's going down. Good grief. From negative 3 to positive infinity. All right, so you can do that one. You can do that one. All right. So now we're going to do ones without graphs. So we've done it with graphs. Now we're going to do it without graphs. So I would like to know the open intervals where my function is increasing or decreasing. So I've got an x squared minus a 4x minus a 32. So we know he's a parabola. We know that he opens upwards because he leads off positive. So he looks somewhat like that. All right, so using calculus, I want to figure out where this thing is going to increase or decrease. So the first thing I want to do is find any places where he is discontinuous. Okay, so are there any variables in denominators? No. Are there any variables under radicals? No. So my domain is all real numbers. Everything is fine. The last thing I need to look at is where does my derivative equal 0? So if I take a derivative and set it equal to 0, which is a critical number, and then solve, I'll add 4 and divide by 2, and I get x equals 2. So we're going to draw a little picture. It's a number line just like from, what, first grade? Okay, so 2 is where this thing equals 0. And I'm going to come up, and I am going to use test points in my original derivative. So that's my first derivative. I set it equal to 0, but I'm going to put test points in there. So any number to the left of 2, there's an infinite number of numbers to the left of 2. I'm going to grab 0 because it's easy to work with. So 2 times 0 is 0, minus 4 is negative. You got a negative slope when you evaluated it to the left of 2. So that means he's decreasing. So give me a nice number to the right of 2. Well, a nice number to the right of 2 is 10. I don't care what it is as long as it's to the right. So 2 times 10 minus 4 is positive. And now if you'll look, you essentially just drew your parabola. So where is he decreasing? He's decreasing from negative infinity to 2. And where is he increasing from 2 to positive infinity? Okay? So let's do another one. We've got 27x minus x to the third. So 27x minus x to the third. So your domain is all real numbers. I don't see any variables in denominators. I don't see any variables under radicals. So I'm going to take a derivative. Minus 3x squared. And I'm going to set it equal to 0. So this is where I'm going to plug in my test points. Okay, that's your first derivative. So if I solve this thing, I'm going to add 3x squared to both sides. Divide by 3. So plus or minus 3 are going to be your critical numbers. So I've got negative 3 and positive 3. So I've got 3 distinct intervals that I need to test. Okay? So a nice friendly number to the left of negative 3 is going to be negative 10. Okay, so 27 minus negative 10 squared is 100. So 27 minus 300 is negative. So he'll be decreasing. A nice friendly number in between here is 0. So 27 minus 0 is positive, so he's increasing. And then use 10. 27 minus 300 is negative, so he's decreasing. So he is decreasing on the intervals from negative infinity to negative 3, and again from 3 to positive infinity. He is increasing on the interval from negative 3 to 3. Okay? So let's find an exciting one. Well, let's do that one. All right, so I have x equals, I am flipping the page. Hang on, where am I at? All right, x equals 36 minus x squared. I did not even say that right. All right, so this is my function. And the first thing I notice is I got some stuff that's off limits, because whatever is underneath that radical, I want it to stay positive. So how do I know what that is? I'm going to take my argument, which is the stuff under the radical, and I'm going to say you've got to stay positive or equal to 0. Okay? And when you work this through, you're going to find out that everything between -6 and +6 is fair game. Okay, if you use -7, then 36 minus 49 is off limits, because it takes you to negatives, which will take you into imaginary numbers. If you use +7, same thing. Okay, so what we know right now is this function only exists between -6 and +6, inclusive of the endpoints. So we know when we start testing points that this thing, I don't need to test anything to the left of -6, because it doesn't exist there. I don't need to test anything to the right of +6, because it doesn't exist there. Okay, so the next thing is take a derivative. So I've got variables times variables, so I need to use product rule. So I've got the first times the derivative of the second. I have to sneeze, hang on. All right. God bless me. All right, so derivative of the second means I have a 1/2, drop your exponent by 1, times the derivative of the inside. So I have first times the derivative of the second plus the second times the derivative of the first, which is 1. All right, so I'm going to clean this up. Remember, that's getting set equal to 0. Okay, I know that this 1/2 and this 2 reduce. I know that this x and this x multiplied together is x squared, and it's negative. So I have a negative x squared over, because this is negative, the square root of 36 minus x squared plus the square root of 36 minus x squared. All right, so now you got a fraction. Well, what numbers can you not use? If I use -6, 36 minus 36 is 0. So if I can use it in my original function, but I cannot use it in my derivative, it means you have a cusp there, or a pointy part. Okay? So if I hadn't already, -6 would be part of the issue. So I would have -6 on my number line. +6, same way. Because now that he's in a denominator, you can't divide by 0. And so I'll have a cusp at -6, and I'll have a cusp at +6. The whole deal is, I want to find out how this thing is going to end up equaling 0. So I am going to add this one to the other side. And I'm actually going to go down here. All right, so I have the square root of 36 minus x squared equals a positive x squared over 36 minus x squared. So I just added this term. Oops, you can't see. I added this term over to the right. And now I'm going to cross multiply. So this chunk times this chunk means it pops out from underneath the radical. And then x squared times 1 is x squared. So I'm going to add x squared. I just said I'm going to add x squared. So I get 2x squareds. So 18 is x squared, because I divided by 2, which means I will get plus or minus 3 square root of 3 is x. Because you take the square root, the 9 comes out and becomes a 3, the 3 stays inside. 2! Good heavens, 2. All right, so 9 times 2. All right, so what we have is, I've got another critical number at -3 root 2, and another critical number at +3 root 2. Okay, so those are your test intervals, and they only exist between -6 and +6. Okay, so where do you test these things at? Test them up in here.